Let's continue with the renormalization of the electroweak standard model. In the last lectures, we discussed the on-shell renormalization scheme, and we gave the conditions, the so-called on-shell renormalization conditions, which fix the finite parts of the renormalization constants, and even more importantly, which fix the physical meaning of the input parameters E, MW, MZ, and so on, and give us equations how we can compute the renormalization constants in terms of loop Feynman diagrams. Today we will talk a lot about the physical implications and the physical meaning of the on-shell renormalization scheme, and at the end of today we will also give an example of how this all works in practice and how loop calculations actually look like and what the important effects are which come into play at higher orders. And so we will begin right now with a section on the physical meaning. And the physical meaning derives from our on-shell renormalization scheme, which provides the definitions of the parameters, but we need to augment our on-shell conditions by Slavnov-Taylor or Watt identities, because without them we cannot understand the physical implications. And that is similar to QED, but as always the structure is quite a bit more complicated, but let us work through it. And the first item is the obvious one, which you know from QED as well, namely the masslessness of the photon. So the point was that in our on-shell conditions we could not impose a condition which requires that the photon is massless. Instead, we had a bunch of other conditions which are kind of related to the photon, but the actual condition that the photon is massless would mean that the renormalized photon self-energy vanishes at zero momentum, and that we couldn't impose because there is no renormalization constant available which could make sure such a condition. Therefore, either the condition is satisfied automatically or it's wrong. And it is satisfied automatically, and that is the result of Slavnov-Taylor identities. And so let us prove that, because obviously it is important for the interpretation of the standard model that we know for sure that the photon is massless, indeed, not only at tree level but at all orders. And so here we use something from the Quantum Field Theory 2 lecture, where we had sections 464 and 465, where we discussed exactly Slavnov-Taylor identities in the context of spontaneously broken gauge theories, where we had this would-be order parameter dAi, which is this two-point function involving a ghost Ca and a source K Hi. So that means the BRS transformation of a scalar field Hi into the gauge direction A. And if that object here is non-zero, then it means that in the vacuum the gauge transformation becomes a non-vanishing constant. In other words, we have spontaneous symmetry breaking. And this is described by those would-be order parameters. I call it would-be order parameter because of this qualification that actually spontaneous symmetry breaking in a gauge theory is kind of a difficult concept. But anyway, the rank of this matrix is what tells us how many spontaneously broken directions there are. So that is the number n broken symmetries. And that is at the same time the number of massless would-be Goldstone bosons. And they are truly massless before we have gauge fixing, but in the context of gauge fixing, the gauge fixing might provide a mass, but we saw in the lecture a precise way how we can disentangle the would-be masslessness of those would-be Goldstone bosons from the effects of the gauge fixing, because we couple the gauge fixing to this auxiliary field B, and so then we could truly speak of massless scalar states. And so that is equal to this number, and it is of course also equal to the number of massive vector bosons. Now, in the standard model at tree level, we know of course what is going on, namely in the standard model at tree level we have 3 spontaneously broken directions and therefore 3 massive gauge bosons and 1 massless photon. So here this n broken is of course 3. So what does that mean for higher orders? In perturbation theory, the higher orders can only affect the lowest order in an infinitesimal amount. And so that means a mass of a state can change by an infinitesimal amount. So a mass which is 0 could become non-zero by an infinitesimal additive piece, but a mass which is non-zero cannot become 0 by adding something infinitesimal. Therefore, the number of massless states could decrease and the number of massive states could increase, but not vice versa. And so that we can use in 2 different ways. So let's write it down. The number of massive massive vector bosons could increase, which in practice means the photon could become massive. In perturbation theory, maybe. And however, the number of massless Goldstone bosons, that could also only increase, could only decrease, or the number of massive Goldstone bosons could increase. But what does it mean? So the number of massive vector bosons could increase. That would mean that the rank would go up from 3 to 4. The number of massless Goldstone bosons could decrease. That would mean that the rank would go down from 3 to 2 or some other smaller number. So the rank cannot simultaneously go up and down. Therefore, it must remain constant. So from one argument, it could only become bigger. From the other argument, it could only become smaller. Both arguments at the same time apply. Therefore, it remains 3. So we can say n broken is on the one hand bigger or equal than 3, and n broken is smaller or equal to 3, and therefore n broken is equal to 3 at all orders. And that is the proof that at all orders there is precisely one and only one massless vector boson in the standard model. Which by definition is then of course the photon. And technically it means that the determinant of the 2-point function matrix at 0 momentum vanishes. So if you look at this matrix, the transverse part of the 2-point function in the space of vector bosons VV prime at p square equals 0, that determinant vanishes at all orders. That is what it means that we have one massless state. Okay, that's it. That is the proof that at all orders the photon is indeed massless, and the photon is defined as the massless direction in this matrix. And let me just add that you can do a similar argument for the unphysical ghosts using the ghost, let's say the 2-point function matrix. that also the determinant of this matrix CA, C bar B at p square equals 0, that determinant also vanishes at all orders, and so there is at all orders one massless ghost. Okay, so that is one important consequence, which is obviously crucial for the correct physical interpretation of the standard model. So you are not surprised by the statement, but it is good to know that you can really prove it at all orders by using the Slavnov-Taylor identity formalism that we have developed. Now we can combine this result with the on-shell renormalization scheme and derive more detailed consequences on the individual self-energies between the various fields that we have in our theory. So that means we go to the interpretation of the on-shell conditions. So, and for most of them, the interpretation is of course obvious because it's the same as in QED, but let us immediately focus on the special on-shell conditions for the mixing vector bosons W and photon and Z boson. And so let us take what we have just derived and look at the photon. So this is section 331 that we just did, plus the on-shell condition has the following combined implication, namely around p square equals 0, we can say, let's say p square equal a small quantity capital delta, which is small. Then what do we know about our transverse self-energies? So this matrix here of transverse two-point functions, gamma AA transverse, gamma AC transverse, gamma CA transverse, gamma CC transverse as a function of p square. How does it look like? Well, what we have imposed as our on-shell condition is that here in the ZZ we have not imposed anything at p square equals 0, so that is something. It is non-zero because it is non-zero at tree level, so it's non-zero at all orders. At tree level it's basically given by the Z mass square. And so here we do not know what happens, but the AEC mixing self-energy, that had an on-shell condition, namely at 0 momentum, that two-point function vanishes. So that means around p square equals 0, we could call this b times delta, where b is the derivative of this object at 0 p square. Okay, and then for this we couldn't impose an on-shell condition, that was the point. And so now we know that the determinant of this matrix at p square equals 0 vanishes. And what does it imply? It implies at p square equals 0, the off-diagonal elements vanish. This diagonal element is definitely non-zero, therefore we know that at p square equals 0, that diagonal element must vanish. And so we conclude that the diagonal two-point function gamma AA in the on-shell scheme vanishes at 0 momentum. So that is now true in the on-shell scheme. And then we can kind of combine all on-shell conditions that we have in terms of this matrix, just to get a visualization maybe. this matrix here, gamma AA, gamma AZ, gamma CA, gamma CZ transverse at around p square equals 0 has now the following form: A times delta, B times delta, B times delta, and some non-vanishing constant C. Okay? And so we know that the on-shell condition tells us that all these objects now vanish at 0 momentum. So for small momenta, we have this at first order in p square. And you now know, and that is interesting, I think, what are fully the 2-point functions, the green functions. The green functions for these in this sector, the 2-point functions are the inverse of that matrix. So it is now of interest to invert actually this matrix, and that gives us information on the full propagator, photon, 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 Z, 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 and so on. So let us really do that in order to see the implication of the on-shell conditions. So the inverse, this matrix of 2-point functions AA, AZ, CA, CZ, that is I times the inverse of that. And what is actually the inverse of that? The inverse of such a 2 by 2 matrix is 1 divided by the determinant times the matrix where you flip the diagonal elements, and the off-diagonal elements get a minus. And then you have 1 over the determinant. And what is the determinant? A delta times C minus B square delta square. So, and then I times 1 over A times C minus B square delta. And then you have here C divided by delta minus B A. I've cancelled one factor of delta. And so delta is p square, and we are looking at this at around p square equals 0, and these are the full 2-point functions after calculating all loop corrections to them. So that includes tree level plus all higher order Feynman diagrams, including renormalization. And so what do you see? Here is the photon propagator, the full propagator including loops. And how does it behave? It behaves like I times C divided by A times C. So it first of all has a pole 1 over delta, 1 over p square. It has a pole at p square equals 0, which corresponds to the photon mass. What is the residue of the photon propagator at 0? C divided by C times A, so that goes to 0 in the limit p square going to 0. So the residue is 1 over A. Photon. Okay, let me add one additional item. Where A, what is actually A? A is the derivative of the 2-point function at 0 momentum, and for that we did have an on-shell condition, namely we said that this residue, this derivative should be 1. That was an on-shell condition. And so therefore A is actually 1 because of the on-shell condition. So therefore the photon propagator behaves around p square equals 0, simply like I divided by delta, I divided by p square. And so it has residue 1 and a pole at p square equals 0. So, and therefore you see that the on-shell renormalization condition really completely fulfills all these simple criteria that we would like to have. So the photon propagator behaves exactly like at tree level at all orders. So that is a very powerful statement, and it means, first of all, the masslessness of the photon is now manifested in this way in terms of the pole, and for actual calculations where we need this LSC reduction formalism to calculate the S matrix, where we would need the residue as a wave function renormalization. The residue is 1, so therefore this wave function renormalization drops out, or it's 1. Therefore, it doesn't have to be separately calculated, which makes it more practical. So that is the thing. You see also some other interesting things which you might memorize. So these off-diagonal 1pi green functions, they vanish at 0 momentum. That was the on-shell condition. However, the mixing propagators AC, they do not really vanish. However, they don't have a pole. It's just they don't have a pole, but they actually do not go to 0 at p square equals 0. So that is maybe something where one might get confused. And the Z propagator at p square equals 0 has no pole. So there is, this is what we call unmixing. So there is, the mixing basically goes to 0. So we have in the system only this 2-point function has a pole at the photon mass, and all the other 3, they are non-zero, but they do not have a pole at the photon mass. So that is very nice. And of course, at the Z mass, exactly the opposite is valid. So let's not go through the calculation, but it is obvious that exactly the opposite renormalization conditions now hold. There, the matrix has the form, let's say, C times B times delta, B times delta, and here A times delta, and again A is equal to 1. So then the Z propagator behaves like 1 divided by p square minus mz square around the Z mass pole, and therefore we have a pole at p square equal mz square, and again the residue is equal to 1. And again you would have mixing propagators which are non-zero, but which do not have a pole. So this first of all gives us full control over those 2-point functions, which are of course extremely important building blocks of the theory. It makes clear how we can calculate scatterings involving those particles, and it also fixes the interpretation of the field operators. Field operators A mu, Z mu directly correspond to the corresponding particles. So the quanta of those field operators are the photon and the Z, as you would expect, and no linear combinations. So in this sense, the on-shell scheme gives us a very clear and kind of direct, obvious interpretation. So this is the most important and most, let's say, interesting, non-obvious part. Let me, however, write down the rest for the other sectors of particles. So similarly, the on-shell scheme guarantees that the W mass is the physical W boson. The residue of the W propagator is 1. And the same is also true for the fermions. Like in QED, the masses MF correspond to the physical pole masses of the particles. All the residues of the propagators are equal to 1. And similarly also for the Higgs sector, for the physical Higgs, MH is the physical pole mass of the Higgs boson, such that the Higgs 2-point function has a pole at mh square, and the residue of the Higgs propagator is also equal to 1. So that we can say in all cases that the field operators correspond directly to the particles in the obvious way, just like at tree level. Furthermore, in the case of the Higgs, since we have this tadpole condition that the one-point function vanishes, that means that all the fields are expanded around the true vacuum. So I refer to our quantum field theory 2 lecture at this point here, so I have a reference. We had section 3 in the quantum field theory 2 lecture, where we said that in the vacuum the one first derivative d gamma with respect to fields at fields equal 0 in the vacuum vanishes. And so here we know that at field value equals 0, the derivative vanishes, and therefore we know that 0 field means we are in the full vacuum of the theory. So in other words, all the physical interpretation of all of our on-shell conditions is fixed in this way, and it is kind of non-surprising interpretation, but it is good to know that we can firmly establish this meaning in that way. Any questions so far? Because now we have dealt with basically all renormalization conditions except for one, and the remaining renormalization condition is the one for the charge, where we already said that this is a little bit complicated, and I dropped Watt identity from which we derived simplification of the renormalization conditions. And that Watt identity is non-obvious. And I told you that its derivation is way more difficult than in QED. And so for the rest of the lecture, we will discuss this charge renormalization problem, which is also a very interesting problem, both for the solid physical interpretation of the standard model, but also from the point of view of understanding how you can use the Slavnov-Taylor identities and related tricks in order to get a grasp on such theories like the standard model. Okay, no questions. Then let us go on. So, as I said, this discussion is more complicated than in QED. And what happened actually in QED, if you remember? In QED, we used a quite simple Watt identity, which was discussed by some of you also yesterday in the seminar. And from that Watt identity, one could directly prove that the renormalization constant, delta E, depends only on the photon propagator. The photon propagator, there is just one photon propagator in the theory, therefore the calculation of delta E is universal, and it drops out which fermion you actually used in order to define the on-shell condition. Electron, muon, tau, whatever you want, in the end the delta E result is always the same. And that implies charge universality in the sense that if you fix an on-shell condition for one fermion, automatically on-shell conditions for all fermions are simultaneously satisfied. In that sense, charge is universal. And so therefore there is a double role, namely on the one hand the technical simplification of the delta E renormalization constant, and second the physical result that all on-shell conditions are simultaneously satisfied, which gives an information on physical measurable cross-sections. In the standard model, we would like to have both as well, And the trick is, and I mean that is now the discovery after decades of work on this, that we should disentangle the two. There is on the one hand the statement of charge universality, which is the physical statement on cross-sections and measurable quantities and S-matrix elements. And there is the second statement on the simplification of the calculation of delta E. And let us therefore discuss both independently. So separate delta E from charge universality. So that means we will first focus on this charge universality, which is the more physical statement. And in that context, we will not really discuss the renormalization constant. And once we have completed that discussion, we can figure out information on the calculation of delta E. Let me therefore give you the physical statement that we want to focus on. So the physical statement is the following. You look at an effective interaction. An effective interaction between the photon and two charged particles, where you have a momentum p and also momentum p coming in, and the photon has momentum q equals 0. So it's a cross or scattering or interaction in general between a low energy or long wavelength photon and a particle which doesn't change its momentum. So it's a scattering in the classical limit. And so this here should be a charged on-shell particle. So, and the set of Feynman diagrams which would contribute here is basically an S-matrix element. So it is really a physical scattering amplitude in this limit of these momenta. And so it is something that can be measured. And the statement is that this is equal to the tree-level result for all charged particles. The tree-level result is given essentially by the universal charge E times the Q of the respective particle. So and here this E is this universal electric charge, which is of course the renormalized parameter E in our on-shell renormalization scheme, but in outside of the on-shell scheme there would be some additional factor here, but that would be the universal charge unit, and that is the quantum number which is prescribed at tree level, which is given by T3 plus the hypercharge of the respective particle. So this is the statement. And so therefore, if you prescribe at tree level what your hypercharge is and what your isospin is, then you know up to the unit of charge exactly how these particles interact with the photon. So particles with the same quantum number Q have exactly the same interaction strength with the photon. And so that covers in particular electron and muon. At tree level, you know, they have the same Q, namely Q is -1. And so then, of course, it's a very non-trivial statement that an on-shell electron and an on-shell muon have exactly the same interaction strength with the photon at these, in this low energy limit. But that is exactly the statement. So even though it's not directly covered by our proof per se, but it's also kind of clear that that would even cover the proton. So the proton is a bound state, but it has also electric charge Q equal to +1. And then again, its interaction strength with the photon at low energy would follow the same line. And therefore, it also has exactly the same interaction strength with the photon as the electron or positron. which means that atoms are exactly electrically neutral, which is obviously a very non-trivial but also very well-tested physical statement. So, some notes about this. We are talking here about a physical quantity. Therefore, the statement is independent of the gauge fixing. This is something that we have not proved ourselves in this semester, but clearly you know that S matrix elements of physical cross-sections are physical processes are gauge independent. And so therefore, if we want to prove this, it would be sufficient to prove it in one particular gauge. The second note is, since the physics also does not depend on the renormalization scheme, only the relationships between observables and input parameters, that depends on the renormalization scheme. But because of that, it is also sufficient to prove it just for the on-shell renormalization scheme. And in this way, we do not have these external wave function renormalizations from LSC reduction. Okay, so this makes it technically simpler. Now let me provide you with a small survey. This problem of charge renormalization has already been discussed very extensively in this long review by Aoki et al. That I gave you from 1980. They have several proofs of charge renormalization. They all call it proof of charge universality, but actually all the different proofs which they give, and they give at least 3 or 4, have slightly different statements, and only one of them covers really exactly this situation. So of simpler or related statements. One of them, let me highlight this one, one of them is also similar to an argument by Weinberg, which is often discussed these days, which you find in Weinberg's textbook and also in the book by Schwarz now, to Weinberg's argument. See in his section 13.1, where he basically shows from infrared divergences and from Lorentz invariance of general amplitudes involving external photons that there must be something like photon couples only to something like electric charge. And this can be used also to derive some sort of charge universality, however not exactly this one that we want here. But anyway, it is interesting to see this connection also. And then they give a proof in Landau gauge for the statement that we actually want. Then in these various papers and books by Denner et al., they also give this proof in Landau gauge, and the formulation that they give is a little bit closer to what we do in the lecture. However, it follows the same line of thought. Let's say maybe a modern presentation. Even though I want to highlight that this old paper by Aoki et al., even though it's maybe not a completely modern presentation, but it contains really a lot of very valuable information. And then by Denner et al., in particular Denner plus Dittmeier, there is a very nice proof in the so-called background field gauge, which is arguably even more elegant than the one in Landau gauge, because it most closely mimics the proof in QED. So this background field gauge is something we have not discussed in the lecture, and we will not do it in this semester, but anyway, it's an elegant choice of gauge fixing, which brings you to a formulation of the theory which closely mimics QED in many respects. And so also this proof then kind of follows the logic in QED. However, here, as you can see from this list, what we will do is the proof in this Landau gauge. So that fixes what we want to do, and therefore we now need to talk a little bit about Landau gauge. And for that, maybe let me clean the blackboard. So, some preliminary remarks. Maybe you are surprised that we now focus on some particular choice of gauge, because gauge fixing is of course something unphysical, and to quite some extent we avoided here discussing too much about these unphysical ingredients like gauge fixing, ghosts and so on, even though it's of course necessary to at least write down the Slavnov-Taylor identity. But it is an experience that one has made over the years in discussing the standard model, and in particular some more formal properties, but also practical calculations, that it is not too bad if you are a little bit versatile in choosing gauges which are optimized for your problem. And why not? I mean, that just means that you are able to simplify your calculation depending on what you want to achieve. And here it is actually not always necessary and useful to do general proofs in completely general gauges and make your life a hell. But on the contrary, it is nice to prove also things in specific gauges when you otherwise afterwards know that you can switch the gauge afterwards. And so the Landau gauge is a particular gauge, is a part of the RxI gauges. We are generally working in this RxI gauge fixing. That is a special point in the family of RxI gauges, so therefore we can do it here easily, because it is contained in what we know. And I want to also highlight this background field gauge, which is another kind of gauge which you can apply if you want to achieve certain things. It has definitely great advantages for certain purposes, but it would take just too long to introduce that. But so I want you to take away from this that it is more general than just looking at Landau gauge. Choose your gauges wisely whenever you want to achieve certain things. Either do a practical loop calculation or do some proofs like we want to do now. So having said this, let me introduce Landau gauge. Landau gauge is simply defined by setting psi equals 0. So and we have psi and zeta gauge fixing parameters. They are now set to 0, and let me in this way write down fully the gauge fixing and ghost terms for this case. So for this case, our gauge fixing and ghost term in total are always the total BRST variation of something, namely anti-ghost C bar times a gauge fixing functional. And previously it was always something like this: psi over 2 b plus some other functional f. And now the psi over 2 times b term is not here, but instead we simply put the gauge fixing term like this: d mu a mu. That's all. that is Landau gauge. Okay? And so that is the ordinary gauge fixing functional. And in the standard model, we would have here plus mass times Goldstone boson, but the mass times Goldstone boson is multiplied by zeta, therefore this is now also absent. So that is as simple as this. So this is really a super simple gauge fixing term. And what results if we work it out? So first of all, we get from here BA times DAA. Okay, just this term with the auxiliary field, minus C bar A times d mu BRS transformation of SA mu. And here, of course, I write it in a generic way with gauge group indices A, and that runs over the 4 gauge bosons that we have in our standard model. So for the photon and Z sector, where it is most interesting, we would have BA times the actual photon, A without index is the photon, plus BZ times DZ with a Z boson field, minus C bar A for the photon ghost times BRS transformation of d mu times the photon field, minus C bar Z times BRS of d mu Z, plus charged terms with the W boson. Now, ordinarily, when you have such a gauge fixing term with B fields, you would then say eliminate the B fields in terms of their equation of motion. Now the equation of motion for B doesn't contain B. The equation of motion for BA simply means d mu A mu equals 0. So that is now really this Lagrange multiplier which imposes an equation. In this case, the equation d mu A mu equals 0 is imposed by the equation of motion. And you cannot eliminate B in terms of its equation of motion, but you would have to set d mu A mu to 0. And so here it is maybe simpler for some purposes to keep the B in the theory. Let us also write down the BRST. And okay, then let's look at this term here. This gives the ordinary gauge kinetic, ghost kinetic terms. So one term here gives us the D'Alembert operator of Faddeev-Popov ghost, and other terms give us interactions between Faddeev-Popov ghosts and gauge bosons. So the ghosts are interacting. It is not a gauge where the ghosts are free and where we can ignore the ghosts. We have non-trivial ghost interactions, but they are way simpler than ordinarily, because ordinarily in the arc-psi gauge we have also ghost interactions with Higgs bosons, which depend on the masses MW, MZ times gauge parameter, and here it is really much simpler than this. So let us also write down the Lagrangian involving the BRST sources, which are those ones here, K A mu times BRS transformation of A mu plus K Z mu BRS transformation of Z mu, plus then also there is this for the Goldstone boson, Kg plus BRS transformation of the Goldstone boson plus all the other ones. And why do I highlight this one? I highlight this one because the BRS transformation of the Goldstone boson is the gauge transformation of the Goldstone. The Goldstone transforms into the vacuum expectation value of the Higgs. That is the point of a Goldstone boson. So this involves in particular the term vacuum expectation value plus Higgs times the Z boson for Faddeev-Popov ghost. So that is the sign of spontaneous symmetry breaking. Then gamma classical, as usual, denotes the classical action, the integral over the. Now, let us write down some special feature of Landau gauge. Namely, let us take the functional derivative of the classical action with respect to the photon ghost at x. So if we do that, then the point is that this is almost linear in the quantum fields. Most terms are linear in the quantum fields, but not all of them. So please search for terms where the photon ghost interacts with a product of other quantum fields. Where are such terms? Or where are linear terms, by the way? Where are linear terms and where are non-linear terms? So here there appears, for example, the ghost. Here the ghost appears. Here everywhere there are ghosts. And where are the linear terms and where are non-linear terms? For example, here in the second line, or who sees any term? Which term are you now looking at? Let's use some colors. So indeed, that term gives us, for example, this indeed, but actually not only that. So the BRS transformation of a gauge field in a non-abelian gauge theory also gives us some other kinds of terms. Namely, there are also terms derivative times products of gauge fields times some other ghosts proportional to the structure constants. Even though it's the photon, but the photon is non-abelian here in the standard model. And so there are such terms. And so if you take the derivative with respect to the ghost, then you get from here a term that would be linear, and from here a term which is actually non-linear. And so therefore, indeed, let us write this down. Terms which have the following form. The derivative can be, by partial derivative, can be put entirely onto the anti-ghost, and then we would have some vector boson with some different group indices, and they would be multiplied with some structure constants. So that is a nonlinear term we get from here. What about the entire second line? Here, for example, there are ghosts, and the ghosts appear either in this form with a derivative or in a product form. But the worst you can get here is a product of a ghost times another field times a source. So here there are at most two dynamical fields. The source is not a quantum field. The source is only a source. So here there are at most two fields. Therefore, after the derivative, there is at most one field. So that is at most linear. Also, this is at most linear, this is at most linear, even there is a constant term here. So all of the terms in the second line are actually linear. And so, long story short, the exactly only terms which are not linear after the derivative are the yellow terms here coming from exactly this point. And all of these terms have this structure, a derivative acting on C bar times a vector boson. So, and we do not even have to care about the precise prefactors of those terms and the precise structure of those terms, because that is enough. We know there is always one derivative acting on some anti-ghost times one vector boson with some prefactors. Now, next, the derivative of the classical action with respect to some B field, let's say BC, that, what is that? That is of course the corresponding gauge boson, so that is here d mu v c mu. And now you see that this term here, which comes out of the derivative there, is somehow connected to a derivative with respect to B. And that can be made precise in the following way. If we take the x integral of the gamma classical with respect to CA of x, then these are linear terms plus a nonlinear term, but if we take the integral over x, then in this term we can do partial integration, and then the derivative acts on the v. Then we have here d mu v mu, which we can write as that derivative. So therefore we have then an x integral times c bar with some index times derivative of gamma classical with respect to bc of x. And so we do not care about the precise prefactors, but we care about the structure, because now we have a structure of an equation where first derivatives of the classical action, some combination of first derivatives of the classical action give linear terms. And this is an equation which has a form similar to Ward and Slavnov-Taylor identities, and we showed in quantum field theory 2 that if we have such an equation with linear terms only, then this automatically holds not only at tree level, but the same equation will also hold at all orders. And that would be different if we had nonlinear terms here, then we would get expectation values of products of fields. But here, this same equation will automatically remain valid also at higher orders. So if such an equation holds at tree level, it also holds at all orders. So small qualification here, unless, for example, one might add counter terms which destroy the equation. So nobody can stop you in principle from adding at one loop level suddenly a counter term which just messes up the equation. But then it means you have control yourself by doing the renormalization prescription. What happens, and then at least the equation would remain valid for the bare Lagrangian before counter terms. So so this is one possibility, and it might contradict the Slavnov-Taylor identity. So in principle, one should prove that this equation is not in contradiction to the Slavnov-Taylor identity, because that is really a defining feature of our theory. If it would contradict the Slavnov-Taylor identity, then we would have to add counter terms which are in agreement with the Slavnov-Taylor identity, but which ruin this equation. But that is not the case. And as a reference, I put here a book by P.G. Sorella, section 6.1, where this is explained. Okay, so therefore we can really simply use here this equation, and at least before adding counter terms, it is for sure valid at all orders. So therefore we know the following. This equation at all orders gamma derivative with respect to CA of x is equal which is, by the way, the same, sorry, I was shortly confused. So we had this already once, and some of you complained about it or made fun of it. So this integral over x is of course the same as in Fourier space at momentum equals 0. So that is always the same as at tree level. So and actually we can even drop those terms here because anyway the derivative with respect to b on its own has already the same property, therefore this also remains always equal to tree level. And so therefore we can simply say the first derivative at 0 momentum with respect to a ghost remains tree level at all orders. And so what it means in simpler terms is if you have a ghost with 0 momentum, it does not appear in loops. There are no loop diagrams connected to a ghost at 0 momentum. So the ghost only interacts in loops at non-zero momentum. That reminds you maybe of Goldstone bosons, which have the same property. And by the way, I used here Ca to be concrete, but the same is true also for the Z boson ghost. Let me give you a small illustration of this. Where you also see the special property of the Landau gauge, or maybe more explicitly. So let us imagine a loop diagram with a Faddeev-Popov ghost. So here there is a Faddeev-Popov ghost coming in, Ca, with momentum equal to 0. Then, as you see from this, the precisely only Feynman rule that a ghost has, which is an interaction, is that the ghost emits a vector boson. This is the Feynman rule coming from this term in the Lagrangian here, which is the standard Faddeev-Popov ghost interaction in a non-abelian gauge theory. So this is the only thing that the ghost can do, and if you now want to have a non-trivial loop, then this vector boson must be part of the loop diagram. If it's external, then you have not one pi Feynman diagram. So that must be here in some loop. Okay, so if this is in some loop, then there must be a loop momentum associated with this vector boson and with that ghost line here as well. Since we have here momentum equals 0, we must have here a loop momentum k, which flows in some direction, and here the same momentum k as well, which flows in some direction. Then, what is the Feynman rule of this vertex? As you know, hopefully, the Feynman rule of such a ghost-ghost vector boson vertex is proportional to the anti-ghost momentum. So this Feynman rule is proportional, let me draw it here. So this Feynman rule here is proportional to k mu, to the anti-ghost momentum. But what is the value of the vector boson propagator? A vector boson propagator in Landau gauge is transverse. Xi equals 0, so we always have this additional term in the propagators like 1 minus xi. So now for xi equals 0, the propagator is simply transverse, which means this. This is how the propagator looks like. So what happens if you hit a transverse propagator with the momentum? You get 0. That is the simple point. So in Landau gauge, in every Feynman diagram with an external Faddeev-Popov ghost, which is 1 pi, you must have this vertex at the beginning of the diagram, and there the momentum hits the propagator, and if the ghost has 0 momentum, these momenta are the same, and therefore the product vanishes. And that is the reason why all loop diagrams with 0 momentum Faddeev-Popov ghosts vanish in Landau gauge. That is the explanation. And the previous proof, or this statement here with this all-order equation, that would become invalid outside of Landau gauge, because outside of Landau gauge, this d gamma derivative with respect to B gives something else, and therefore you cannot write the nonlinear terms as a derivative with respect to B, and therefore there is no such equation valid outside of Landau gauge. And so therefore it all fits, and so both of these discussions show you that Landau gauge is particularly simple with respect to the loops from Faddeev-Popov ghosts. Very good. Now let us write down also a few more smaller simple statements. So let me write down something about the renormalization transformation. So in general, we have the following. So photon Z goes to square root of this Z matrix, 2 by 2 matrix A to Z, and the B fields, they transform in the opposite way with the inverse Z factor matrix to the -1. Also the anti-ghosts, they transform like the B fields. And also the sources, they also transform like the B fields, such that the gauge fixing term overall does not renormalize, and the product of source times field also does not renormalize. And the ghosts, CA, CZ, they transform with a different matrix, let's call it Z tilde times CA CZ. Here, let us now choose this Z tilde such that the counter term Lagrangian does not introduce mixing terms of CA and CZ. So the CA should couple only as at 3 level. For example, if we would, let's say, calculate in terms of unrenormalized CA and CZ, that would be satisfied. Otherwise, you should choose this Z tilde matrix accordingly, and then we will draw our consequences on charge universality. So, the relevant green functions are the following. So let me give you first a list. So these are green functions involving different sources for BRS transformations and for Faddeev-Popov ghost. So they tell us how various fields like the Goldstone boson or the gauge bosons gauge transform under QED gauge transformations, because remember the ghost denotes the direction in which we perform a gauge transformation, and so derivatives with respect to this ghost would be the counterpart of QED gauge transformations. So these building blocks here would effectively tell us something about the QED gauge transformations of all the various fields. Then we have further green functions involving CA. So the self-energy, mixing self-energy between CA and CZ bar. And then finally, and very importantly, this sort of thing, which again tells us how a field psi gauge transforms in the QED gauge transformation direction. So that would be effectively like the charge, the electric charge of a particle psi or a field psi for some fields psi. Now, let me, sorry, I was confused about the time. So we still have a little bit of time. Let us write down some conclusions and consequences of this all-order equation together with that small assumption here, which I formulated in a little bit vague terms, but now it becomes precise. Namely, so the gauge transformation of the Goldstone boson in the direction of QED. That is the interpretation of this green function. What is its value? First, what is the value at tree level, and then what are the higher order corrections? So at tree level, the Goldstone boson has a non-trivial gauge transformation, of course. It is SU2 doublet and hypercharge non-zero, therefore it has non-trivial gauge transformations in all directions. And in particular, the Goldstone boson transforms into the Higgs field plus its vacuum expectation value. But what does the Goldstone boson, the neutral Goldstone boson, do if you do an electromagnetic U1 electromagnetic gauge transformation? It doesn't do anything because it's electrically neutral. So under QED gauge transformations, the neutral Goldstone does not transform, and therefore this green function at tree level is zero. What is not zero is the thing with the Z boson here, because with respect to the Z, the Goldstone boson transforms into the Higgs plus vacuum expectation value, as we already mentioned before. But this green function is zero at tree level, and now we choose our counter terms such that there is no mixing, no additional mixing between the two ghosts. Therefore, there are no counter terms by this assumption and requirement on the procedure, which would ruin this. And we have the all-order equation that there are no loops at zero momentum. Therefore, the loops cannot mess up this equation because it's zero momentum. And therefore, we know that this is exactly zero at all orders. Similarly, our ghost self-energies, they are of course zero. So here the on-shell condition is even simpler because all the ghosts are zero mass states. So therefore at zero momentum this is automatic. And similarly, and that is now important, this green function here. If we have this 3-point function, which basically means BRS transformation of some fermion psi into QED direction and itself, so that basically corresponds to the electric charge of that fermion. At tree level, this will be proportional to the electric charge of that fermion. And we put the ghost momentum to zero, therefore again there are no loop corrections, and because of that requirement there are no counter term corrections, and therefore this is always equal to tree level. And at tree level it is proportional to the charge of the field psi times E. So this is what we can use. Now the question is, do we have enough time? Yes, I think we have enough time to to draw some further consequences from the Slavnov-Taylor identity. So now it becomes serious. This is all preliminary work, or maybe not so preliminary, because we have used this non-trivial property of Landau gauge, which is of course crucial. But now we make use of the Slavnov-Taylor identity to draw further consequences. So let's write down the following, namely the second derivative with respect to the photon ghost and with respect to the Z boson field of our Slavnov-Taylor identity in this star notation, gamma star gamma. What do we obtain from this if we set all the fields to 0 after taking the derivative? So there are a few non-vanishing terms. So one term is obtained from this here. Remember that each term in this star notation has a structure. One gamma has a derivative with respect to a source, the other gamma has a derivative with respect to the corresponding field. So in this there would be this combination, two derivatives of gamma with respect to those two objects. And now we apply these two additional derivatives and we can distribute them like this. Then we get two green functions which make sense in terms of ghost number conservation and Lorentz invariance. So here we have a ordinary gauge boson self-energy, and here we have something like over there, namely BRS transformation of the photon goes into the photon ghost. Plus other terms, so there is something similar with the Z. Okay. And then we distribute the additional derivatives like this, and then we have here the Z boson self-energy, and here this green function with source and Faddeev-Popov ghost. What else do we have? Anything else? Yes, indeed. In the standard model we have something else, namely, and we should never forget about that, the gauge bosons can mix with the Goldstone bosons. And so there is now also this term where we get, let's say, derivative with respect to the Goldstone boson and the source of the Goldstone boson, and then we can distribute the derivatives like this. And then we have here a mixing self-energy between Goldstone and Z boson, which is non-zero in general, and here we have such a two-point function. But that's really all there is. And now let us discuss the behavior of all the three terms around p square equals 0, or around p equals 0. So all the green functions have momentum arguments in momentum space. So let's say p minus p, p, and so on. The arguments are always the same, and let's say p is small. Then what do we know about the green function? For example, this one here was 0 at p square equals 0. That is what we set over there on the left. So therefore this vanishes like p square. This here contains one external Lorentz index. Therefore clearly it must contain one factor of p mu. So therefore this term is order p to the third power. So p square times p mu. Maybe let's write it like this. P square times p mu at least. So it goes to the 0 in the third power of p. Now what about this term here? The Z boson. At tree level, you know that one term in this two-point function is simply the Z mass square. Mz square times g mu nu. That is one term that appears here. Mz square times g mu nu. So that does not go to 0 for p square equals 0. It's just a constant. So therefore there is one term here that would go like mz square and then maybe times p nu from here. And so therefore it behaves like that. Then this term, what is this? Here we have the photon Z mixing. In the on-shell scheme that is 0 at p square equals 0. Therefore we have here p square, because at p square equals 0 it vanishes, and then we have here an external momentum at least, so therefore we have p mu times p square. So therefore the first line definitely vanishes like p to the third power, last line vanishes like p to the third power. The second line contains one term which only goes to 0 as p. So, but the equation overall, the sum is 0. That means that this term in the second line actually cannot contain a term that goes like this. Therefore, it means that this term which potentially exists in the second line must actually be 0. And that tells us something about one of the two green functions in the second line. What does it tell us about the green functions in the second line? We know that this is definitely equal to mz square plus higher orders, so that is something we definitely know for sure. If we know that the whole product of the two must vanish like p to the third power, it means that this object here itself must behave like p to the third power. It cannot behave just like p, it must behave like p to the third power. Therefore we know now this outcome. So it first of all can be written like this. So I introduce a covariant decomposition where I write this object as p nu times a longitudinal object which only depends on p square, and then this longitudinal object which only depends on p square vanishes. So this is what we learn from the Slavnov-Taylor identity. So this object here vanishes at 0 momentum. And this object corresponds somehow to a mixing between the photon and Z sector. So in a certain sense, this particular kind of mixing, which is difficult to interpret, but anyway it is 0. So it's a technical expression of the absence of mixing between the photon and Z in one particular type of green functions. And that is an ingredient that we have to use in our proof of charge universality. So I think time is up for the morning. Yes, so okay, we have also actually achieved what I wanted to achieve. Time is up for the morning, and in the afternoon we will go on and we will use exactly what is written here, in particular this one, to prove charge universality in Landau gauge. And then we have an important physics statement. Afterwards we will go on to the other aspect of charge renormalization, where we discuss the simplification on the delta E renormalization constant, and then we will do some physics applications, and that is then the end of the semester. Okay, so see you in the afternoon.